Today we will discuss the conservation of mechanical energy. Whenever we say mechanical energy, we're talking about, for these problems, we'll be dealing only with mechanical energy in the form of potential, gravitational, and kinetic. So no new forms of energy here. What we're going to say here is that in a closed system, meaning a system that does not have any kind of outside work being done on it, no energy coming in from the outside, that the total energy of a system is going to be conserved. It's a fundamental idea in science that energy is conserved, it doesn't just come out of nowhere. So we're going to say that as things go through these processes, we're going to see that their total energy doesn't change. Therefore, the total mechanical energy that an object has is its potential plus its kinetic. And so we're basically saying that if you change its potential to some new potential, its kinetic is also going to have to change as well. So that the sum of the potential and kinetic before and after is always going to be constant. So, as we mentioned before, as long as no work is done no work is done on the system by some sort of outside agent. So the first example, pretty straightforward problem. We've done problems like these in the past using a different approach, but we can solve things in all sorts of different ways using different physics approaches. So the question involves a coconut, so we're going to throw it vertically, and it's going to go, its initial velocity is going to go 25 meters per second, and it's 5 kilograms. So, question is, how high is it going to go? Now we could do this using VF equals VI plus AT, but we're going to take a little bit of a different approach here. We're going to use the conservation of energy. So let's just assume that this starts at the ground level for some reason. And so if we, consider it before, as it begins to move, so it's on the ground, so its potential energy at the beginning is 0 because its height is 0. So the potential before is 0. The kinetic energy before is 1/2 mv squared. So before we have a total energy U plus K of 0 plus 1/2 mv squared. So 1/2 of the mass is 5 and the velocity is 25, so we're going to square that, and that gives us a total kinetic energy at the beginning of 1,560. We'll just call it 1560. And so we know that from what we said on the previous page that that's 1560 is going to equal the sum of the potential and the kinetic when it reaches, well, really at any point. We could actually use this at any point, but the question is asking me how high it will go. So it's going to keep going until its velocity gets smaller and smaller and smaller and then stops. So at the top, when it stops, we know that its velocity is 0 meters per second. So at the top, so this is the bottom, this is the bottom here, and this is the top. At the top, the kinetic energy is actually going to be 1/2 mv squared, which is 0. Therefore, we know that the zeros just drop out, and we know that at the top, the gravitational potential at the end, U prime, is 1560. So we know now that at the top it has a potential energy U of 1,560. So we can set that equal to mgh to get the height. So we're going to divide out mg from both sides and get a height of I'm going to divide mg over here, but let's plug in the actual numbers. M is 5 and g is 9.8. So 1560 divided by 5 divided by 9.8 is, we'll round that to 2 sig figs and call that 32 meters. Oops, that's not the velocity, that's the height. The height is 32 meters. So this, in this example, that would go 32 meters high, which is the same answer that we would have gotten had we done it with the old formulas, but just a different way to get it. And moreover, we also know the kinetic plus potential. If I wanted to know the U plus K for this intermediate step in between, I would know that it was 1560 also, because it was 1560 here, it's 1560 here, and it's 1560 here. But here it's all kinetic, here it's all potential. If this were to fall back down, then the process would be reversed and it would turn that potential back into kinetic. But here in the middle it would have both. So we could actually find the velocity anywhere in between if we knew the height anywhere in between, or vice versa. If we knew the height, the velocity, we could find the height. So this next example problem that we're going to do, roller coasters. You can do a lot with roller coasters on these problems. Oh, by the way, I want to point this out before we get going. Jump the gun there. One thing that ended up, you'll notice if we had done this the old way with our old formulas, we wouldn't have used the mass. We never used the mass to find out how high things went. And in fact, we didn't need the mass here either, but I'll show that to you in this next problem. So let's take this example here. We have a roller coaster, and I've kind of isolated 3 different spots on the coaster that we're going to be interested in. We have spot A at the top, spot B at the bottom, and spot C somewhere in between. Now I've given all of the heights of all of these various points relative to the ground. We're going to use the ground, the actual ground, as our 0, as our reference level. And what I'm going to show you is that we can find the potential, the kinetic, and the velocity at all 3 of these spots, given only the heights and given the mass of the coaster and the original velocity of the coaster. Now I forgot to give you a mass, but we'll just make a nice, easy to work with mass of a ton. We'll pretend it has 4 sig figs. So let's go ahead and find all of these things. We'll start at part A. Part A, U equals mgh, right? So for part A, it is mgh, so m is 1,000. G is 9.8, and the height is 40 meters, so that's very straightforward. So 1,000 times 9.8 times 40 is 392,000 joules. We're also told at the beginning in the first part of the problem that the coaster is not yet moving. It's got a velocity of 0, so that makes the kinetic rather easy to find. That is 0 joules, and the velocity was 0 joules as well. Wait, joules. No, silly. 0 meters per second. So that's pretty straightforward. That's kind of starts out the problem. So then we get to the second part, part B. Whenever it's down in this valley, how fast it's going to go. Now we know intuitively it's going to be going a lot faster than 0. We're assuming that this was kind of like being held up here, ready to go. It just kind of was on the edge, was allow gravity to take it down the ramp. Also, we're assuming no friction, of course, things like that. So in part B, the potential energy we actually can find because it's going to be mgh again. And this time we still have the mass is still 1,000. The gravity is still 9.8, but this time the height is only 10. So we can, it's going to be 98,000 is the potential there. And so how are we going to get the kinetic there, because we don't know its velocity? Well, now this is where the conservation law comes in. We know that the total energy U plus K at part A has to be equal to the total energy U plus K at part B. And we just found U plus K at part A. It's 392,000 plus 0. So at part B, we just found U, it's 98,000 plus K. And so K must be whatever the difference is there. So we're going to take 392,000 and subtract off the 98,000. And there we go. Kinetic energy at point B is 294,000. Should have used kilojoules so I didn't have to write so many zeros. And then lastly, we're wanting to know, not lastly, but lastly for part B, we want the velocity. Well, how fast is it going as it gets to the bottom of part B here? Well, that's pretty straightforward now because we have the kinetic. We know that the kinetic energy is 294,000. So we can just set that equal to 1/2 mv squared and solve. So half of 1,000 is 500. So let's divide that by 500 and then take the square root. And so the square root of 294,000 over 500 is 24.2. So the velocity is 24.2 meters per second. And finally, for part C, we can kind of do this in exactly the same way we did that. So the let's see if I can write small enough here. 245,000 is the potential, and I'm not actually working this one out with you. I'm just giving you the answers so you can try that on your own. 245,000 and then 147,000, and for the velocity at part C, we are looking at, should have worked these out before, but I wasn't thinking ahead. That's 17.1 meters per second. Now I want to do a real interesting thing here that's going to be really important as we go forward, and that is I want to rework part B. Let's start over with part B, and let's change, I want to find the velocity, what the velocity at part B would have been if if you had like taken half of these roller coaster carts off and it only had a 500 kilogram mass. So the question now is how fast would it be going at part B if the mass were half? So let's go ahead and just kind of recalculate that real quick here. So if we go back, we basically, to get these numbers, we had to kind of start with this number. So I had to do part A and B again. So part A, we have 392,000. Whoa, no we don't. We have mu equals mu mg, so 500, or mu mg, and the force of friction, mgh, there we go. 500 times 9.8 times 40, kind of just redoing this number. Well, let's just be honest with ourselves. It's going to be half of what it was a minute ago, right? It's going to be half of what it was a minute ago because it's the same calculation but with half as big a mass. So we got 196,000. All right. So at part B, then, our new total is, that is U plus K. That number, that's the new number that will be the same throughout the problem. So 196,000 joules is the total. At part B now with our updated totals, now this number, again, we're kind of finding it the same way, except it's with half as big a mass, and now it's 49,000 joules. And therefore, when we find the new kinetic, we're going to subtract this total minus the kinetic. So remember that the potential plus kinetic at part A equals the potential plus kinetic at part B. This is 196,000, and this is now 49,000 plus the kinetic. So let's take 196,000, drop to zero there. 196,000 minus 49,000 gives us, that's not right, 196,000 minus 49,000 is 147,000. So the K is 147,000. Okay, so that would be this new number if it were all halved. And finally, now let's find the mass, or I'm sorry, the velocity. So this equals 1/2 of m v squared. So we're going to now take this divided by 250 and square root it. 147,000 divided by 250, square root of the answer is 24.2. What? Apparently the mass didn't matter, did it? And in fact, the mass never matters in problems like these to find the velocity. Assuming no friction, the velocity of a 500 or a 1,000 or a 20 billion, well, other factors may become important then. But generally speaking, the mass of this is not going to affect the speed at the bottom. It's only going to affect the energy. So all of the energy numbers will change whenever you change the masses, but the velocity numbers will not. So there you go.